Hey everyone, and welcome to today's graph reading group.
About topological deep learning by Mustafa Hajij.
Okay, thank you for having me here. Thank you so much, Hannes. Thank you everybody for being here. So today I'm going to talk about topological deep learning going beyond graph data. So this work is a collaboration with really awesome group of people. And it's a lot of work, and it's cannot be done without really the collective hard work and smartness for all my collaborators. So Gada, Theo, Nina, Aldo, Karthi, Tolga, Tamal, Soham, Sharias, Neil, Robin, Paul, and Michael. And there are from they contribute. I'm going to mention their contribution as I'm going in this, but again, so I'd like to first and foremost thank all my collaboration for the awesome work that they have done towards this work. So today I'm going to talk about deep learning on topological spaces, and we spent quite a lot of time trying to explain why should we care about deep learning on topological spaces. This is going to quite naturally bring us to higher order relations. My higher order relations are going to explain some of the most common spaces that we are going, topological spaces that we're going to execute our deep learning on them, like simplicial complexes, subcomplexes. We're going to also introduce a new type of complexes called combinatorial complexes. And on the top of combinatorial complexes, we're going to build our neural networks. And finally, I think that's the most exciting, in my opinion, that's the most exciting part about our work, is that we released 3 comprehensive libraries to do deep learning on topological spaces. And we made them quite accessible, quite very similar to existing packages like Python Geometric, Network X, and such. So I hope I'm going to get time to get to talk about all of those exciting stuff today. Okay, so so in a nutshell, what are topological spaces? So we already are familiar with examples of topological spaces. So sequences and images are the form grids, and they are the most plain and simple topological spaces. A more interesting and complicated topological spaces are graphs. So you have nodes and connection between them. So these are also examples of topological spaces, but you can go beyond graphs to images and simplicial complexes, even cubical complexes. So you can think about cubical complexes as going beyond the triangles, basically. So here in simplicial complexes, you have nodes, edges, and faces, but triangular edges, triangular faces. And in cubical complexes, you can go to faces that have 4 sides and 5 sides and so on. And if you want to go even more general, you can talk about cellular complexes. So cellular complexes, you don't even need to have regular faces like the same way you have over here. It can even go beyond that to hypergraphs. Today we're going to talk about even more general class of topological spaces where we can execute our deep learning framework on. So the main question that motivates this work is how can we define a deep learning framework on topological spaces that naturally extends deep learning models on graphs and images. The extension part is very important. We don't want to deviate. We don't want to just go define this for theoretical purposes. We want to be part of the current literature. We want to extend the frameworks that people are familiar with, and go from there and execute current models as special case of our models, basically. So the most obvious reason why you want to do that is multimodality. So multimodality starts to gain a lot of interest recently. So they found one model basically that can execute various types of data, not only images and sequences. Hopefully, all types of data can be executed if given this topological framework. Other reasons. Basically, probably people who are here are familiar with geometric deep learning. So on graphs, you basically have data that's supported on nodes and edges, but data can be supported on higher order elements of your space as well. So here in this example, in computer graphics, a lot of time you might have a vector field that's supported on the faces. So you have a vector field maybe that represents the hair of the character. So in that case, you might want to infer or learn data on the faces. A lot of time in computer graphics, you might have the data support the label itself supported on the face. So here in this case for this horse, we have a horse segmentation, and the label for the faces, the labels for the segmentation is supported on the faces. So data can be naturally supported on higher order elements. So you might want to infer or learn that. Also, a lot of time also whenever you try to process data or store data, say in a physical system, you might nodes and edges might not be sufficient. Basically, so for here we were giving an example. So people have used graph neural networks to simulate fluids. And so in this case, the state for the fluid is stored on the nodes of the graph. And message passing can be used basically to update the states on the nodes of the graph. If you want to go for a cloth simulation, however, nodes are not enough to store the physical state for the cloth. In that case, you might want to store part of the state on the nodes and part of the state on the edges. So in this case, if you want to do message passing, your graph message passing is not sufficient. So here you need to do message passing between edge and edge using faces. So hence, classical message passing or graph-based message passing is not sufficient to basically update the state anymore for something like this. So here, topological message passing comes to help with or higher order message passing can come to help basically to execute to update the states on the edges and not only on the nodes. So that's the second reason. One also of the reasons that we justified in the paper is the hierarchy of relationships, basically. So if you have this is a common theme even in topological data analysis. So if you have a space over here, then you can think about the coarsening of this space here, which can be, you can think about it as a cover here. So if you are familiar with Mapper, kind of doing something similar to Mapper over here, we could think about those superclusters as being higher order relationships, basically. So you can think about this basically as a hypergraph, if you like. And you can continue doing something like this and basically add relationship among the relationships. That's another reason why you might want to consider higher order relationships while you're studying your data, basically giving summarization of the data of your data. And this naturally here corresponds to the idea of pooling, which is a common theme also that people try to generalize whenever they try to do deep learning framework on certain space. Another reason that we also justified in the paper, this is a common problem in graph neural networks. Whenever you're trying to do graph-based message passing, you encounter the over-smoothing problem. And one way to get rid of this problem is basically to lift your signal to a higher order cell. So it's like kind of teleport your signal from in all those nodes to basically a higher order cell, and then take that. So this is like a message passing basically from the nodes to this higher order cell, and then you can come back from this higher order cell to back to the nodes. So this way here, you go from X to Y in 2 steps versus multiple steps in the binary case. There are other examples in the literature. So for instance, people have used the higher order relationships to basically induce certain inductive bias on, for learning on graphs. So if you just care about graphs, you don't want to move beyond graphs, you might also want to consider higher order relationships as a way to induce some inductive bias to improve some learning tasks on graphs. So you might want to add faces or triangles or cells of any form if you like, in order to improve the learning task. So there are so many reasons, whether you care about topological spaces for their own sake, or care about graph neural networks, you might also want to consider higher order relationships for your learning task. Okay, so first of I've been talking about the notion of relationships and neighborhoods and all those stuff. So I want just to give a general definition so that so right now, moving a little bit beyond intuition, I'm going to start to be a little bit more concrete about the things I'm going to explain. So what do I mean by neighborhood? What do I mean by relationships exactly? So I'll explain all those notions in more precisely. So here I have a node and I have collection of points. So here I don't have a notion of neighborhood for that red points. So the most obvious way to start talking about a neighborhood in a discrete sense is to introduce edges, and that edges here can give me, for instance, the one-hop neighborhood for this graph. But this choice is very arbitrary in a sense, because you can really choose the 2-hop neighborhood. You may want to add faces, triangles, and declare all the nodes that share triangles to be the neighbor for that vertex. And you may want to form, I don't know, like a face of any face that's adjacent to basically to this node to be your neighbor. So really the choice for a neighborhood is arbitrary, so it's up to your learning task. So a neighborhood function, given this basically in the general sense, is just a function from the set S, which is the set of entities that you want to execute your deep learning on, to the power set. So this one, I'm going to just call this the neighborhood of n of x is going to be just the neighborhood of x, basically. So graphs, we agree that the graph are not sub. So we're gonna we basically characterize the main elements for to generalize the relationships to higher order to new domains. So we found that there are basically 2 types of relationships. The hierarchical, we classify those relationships as hierarchical relations and set type relations. So by hierarchical relations, maybe the best way to explain it is by an example. So on simplicial complexes, you have 1 relationships, which are the edges, and triangles form 2 relationships, with tetrahedra form 3 relationships, and so on. So this is also the same case for cellular complexes. So cellular complexes, the dimension of the cell, you can think about it as being the hierarchy for that cell. So you have 1-dimensional cell, 2-dimensional cell, the face, and so on and so forth. So these are, we call those hierarchical type complexes, but there are also hypergraphs, on the other hand, don't have this hierarchy. They allow for arbitrary set type relations, if you like. So we distinguish between these 2 basically type of complexes. So this type of complexes here have hierarchy, but doesn't allow this flexibility. Here you must have triangles. Here's once you have a face, you must have its boundary. You don't have a choice. You cannot have a missing edge for certain complexes. But for hypergraphs, you're missing the hierarchy. On the other hand, you're allowing for this flexibility, but you're missing the hierarchy. In order to define our unifying framework, if you like, we wanted a complex basically that generalize both hypergraphs and cell complexes, and that basically gave us combinatorial complexes. So here I'm giving just the formal definition for those characterization that I mentioned, which are the rank function and the set type relations. So the rank function is going to be just a function from a subset of the power set of S that basically preserves that's order preserving. So if X is contained in Y, then the rank of X is less than the rank of Y. And the set type of relations basically says that the existing of a subset or a relation is not implied by another relation in the domain. Okay, so simplicial complexes and cell complexes are naturally equipped with rank functions, and hypergraphs are equipped with set type relations. Okay, so combinatorial complexes basically have both desirable characteristics. So they have a rank function, but they also allow for set type relations. So we call this space here a combinatorial complex, and that basically form the space upon which we build our framework. So here we give a summary between and comparison between hypergraphs, cell complexes, simplicial complexes, and combinatorial complexes. And so combinatorial complexes satisfy the hierarchy, the set type relationships, and the rank does not imply the cardinality. So as in a simplicial complex, for instance, if you have the rank of the cell implies immediately what cardinality it is, basically. So this is comparison between those common types, common spaces. Obviously, graphs doesn't satisfy any of these. So the formal definition for combinatorial complexes should not be a surprise right now. So you have a triplet, which is S, a set, and X, a subset of the power set, and a rank function. And the rank function just preserve the order. We also find that it's important to add the singularities also to X. So this is just for formal reasons. Like definitions are much cleaner if you add the singularity also as a relationships, as a relation to set of relations X, basically. Any questions so far?
All set from my side.
Okay, please go ahead.
No, I'm all set from my side.
Oh, okay, okay. All right. Okay, so let me just go a little bit in more details about combinatorial complexes, just in case you did not get the intuition. Let me give more intuition about this, just to show you how other complexes fit into this. So this is the simplest type. Maybe here you have a combinatorial complexes with 3 nodes. So you have the pink. By the way, all the complexes here are color-coded. So pink here is going to always be 1-dimensional rank, and blue is going to be 2-dimensional rank. Okay, so here you have this face. You can think about it as maybe simplicial complexes with 2 missing edges. So simplicial complex doesn't allow for something like this. So here we have the hierarchy, and we also have the flexibility in the relationships. Here you have a graph, if you like, if you are from the graph world, and maybe you have, for your learning task, you might want to add again those higher order cells just for inductive bias reasons. You can add as many ranks as you want. So here you have a combinatorial complex of dimension 4, because you have 0 cells, 1 cells. The blue cells is this 2, and then you have 3 cells, which are the green ones. So these are more examples of combinatorial complexes. We also find it important to define a combinatorial complex homomorphism because you need to lift your data basically meaningfully from graphs, simplicial complexes, cellular complexes to combinatorial complexes. So a combinatorial complex homomorphism should not be surprising. It's just it should if x and y is in x1 and if x is contained in y, then f of x must be contained in y and f of y. And this second condition here, we basically wanted CC homomorphism to be a generalization for simplicial maps, basically. And this turned out, the second condition turned out to be important if you want that to be the case, basically. So here, you can think about this map over here as gluing 1 and 3 together towards A. Okay, so here, this map here squashes 1 and 3 together towards A and keep maps 2 to B and 4 to C. Okay, so we're trying to mimic basically the continuous deformation that you might want to do on combinatorial complexes with this function over here.
If you go back a slide,
okay,
then we have in the chat the question: can't all of these cellular complexes also be represented by graphs with different types of edges?
Yes, the answer, we actually had a lot of the quite a long extensive chapter on in the paper how Hajij graph basically can represent all those higher order stuff, basically. So a Hajij graph is a directed graph whose nodes are the cells. So you can have the 0 cells to be at the bottom, and then the edges to be on the second level, and the rank 2 on the third level, and so on. So you can have basically a cascade of nodes, and they start connecting the edges based on this partial order relationships. So Hajij graph definitely can represent all higher order stuff, even this CC here that we mentioned. But whenever you are going to talk about there are certain computation, there are certain you're going to see. I'm going to justify the need for higher order for different type of complexes other than graphs, basically. Whenever I'm going to talk about the network that we can build using higher order relationships that are that are difficult to execute naturally on graphs, basically.
Okay.
Yeah,
okay.
yeah,
well,
I'll explain the lifting. Yeah, but the short answer, yes, every combinatorial complex, all complexes can be converted to a directed graph called the Hajij graph, and that's not only the only graph that can be converted. Okay, so the short answer is yes, it can be converted, but I will justify the need for higher order complexes in the lifting place. Yes, the lifting process. So the easiest lifting process is probably the embedding. So you have a graph over here, and if you, for some reason, that you want to equip that graph with higher order relationships, because you think those relationships they form a meaning in your learning task. So, for instance, Budnar considered equipping every adding basically cells to rings in a zinc graph. So you have here this face over here. You can add maybe a higher order cell, and that turned out to improve the learning task. So other people in the hypergraph community just took this graph here, just get rid of the edges, and then they considered the hyper edges in the graph, and that also improve the learning task. So they can move with those lifting. Basically, you can move from lower order complex to a higher order one. You may want to keep the old relationships, or you may want to get rid of them. So here, yeah, in this case, in both of those cases, we kept basically the old relationships. So you can talk about combinatorial complex. So this is just for you have here this very simple combinatorial complex. We can have this very any basically you're restricted on any subset of it, and that's also going to give you a subcombinatorial complex. And then I told you that we're going to use this basically to define a general way to define a neighborhood on a set. So basically, it's probably easier to explain this with an example. So let me just skip this because there is a lot of notation here. Maybe let me skip it and just show you what I mean over here by this picture. So basically, given any cell, we want to define meaningfully what it means by neighbors of that cell. So this cell can be one-dimensional, two-dimensional, three-dimensional, and so on and so forth. You can define the neighborhood for that cell to be basically any subset that you care about in your space. So here I have multiple examples for this. So this dark cell X over here they can define the neighborhood to be those faces. This edge here, the neighbors to be the co-adjacent faces. This node to be the neighbors of it to be all the edges and so on. So this corresponds. We also showed in the paper how this there is a correspondence between this definition for neighborhood functions basically and classical topology basically. So we basically went back to the literature, the old literature, and we gave the continuous neighborhood definition for topological spaces in a way that's very similar to the way we define it on combinatorial complexes, just to show the correspondence between classical topological spaces and discrete ones. So you can define all types of neighborhoods. In practice, you want to decode the neighborhood function using matrices. So we defined inspired by graphs, hypergraphs, combinatorial complexes, by cell complexes and simplicial complexes. We define down incidence, up incidence, co-adjacency, adjacency, Laplacian, down Laplacian, up Laplacian. All those notions can be defined for combinatorial complexes. So I'm going to talk about some of them over here, just for completeness. So here in this example, this is a simplicial complex. So you have a vertex set. I have those 5 vertices, and they have the edges to be all those edges over here, and the faces, and so on. So I have 2 faces over here. In the combinatorial complexes, to define the boundary, you need actually two indices. So in this case here, I have the 0 index and the 1 index, but I can define the boundary between 0 and 2 and 0 and 5, depending on how much dimension I have. So here, the incidence between 0 and 1 is basically just 1 or -1 based if the edge is incident to the vertex. So here 5 or 4 is incident to 4, 5, 4 edge is incident to the node 4 and then the node 5. And the same thing over here. So B1, 2. So defining here the boundary or the incidence between the faces and the edges. But you can also define the incidence between vertices and faces as well, same way. Okay, so if you are familiar also with Hodge theory, you can define the up Laplacian and the down Laplacian, and those can be defined using the incidence matrices. So the up Laplacian can be defined as just B12, B12 transpose. So basically, just take through these matrices and multiply them and get the up Laplacian, which describe the relationships, the higher order relationships, the adjacency relationships between edges in this case. I can define the down Laplacian as well. So here I'm defining the down Laplacian between faces. So here two faces are related basically if they are or co-adjacent if they are related by an edge. So that's what the down Laplacian here describes. And the Laplacian, the Hodge Laplacian is defined to be the summation of the down Laplacian and the up Laplacian. So if you are familiar with Hodge theory, the Hodge Laplacian basically gives you a way to do Fourier type analysis on higher order networks. We have ways basically to describe the connectivity between elements in a combinatorial complex, which basically described by those matrices that I mentioned, the incidence matrices, the adjacency matrices, the Laplacians, and so on and so forth. We also, in a deep learning setting, you also need data. So there's a fancy word for it in our setting here called code chain, but code chain here doesn't mean anything more than just data supported on your higher order relations. So data supported on nodes called zero chain. Data supported on edges is called one code chain, and data supported on faces called two code chain. Okay, so this is it doesn't mean anything beyond just your feature vectors on your higher orders relations. So you need so we have the complexes, we have the data supported on them. Then you need to shuffle data around. So how would you shuffle data around? Well, you use the same connectivities that we just mentioned. Just to abstract things, let's just look at things from far away right now. This is going to become the bread and butter for our work. So we're not going to view those neighborhood functions or neighborhood matrices that I showed you earlier as way to describe the connectivity. We're going to view them as map that sends code chain from one place to the other. So the adjacency matrix on graphs, for instance, you can view it as a map, as a function that sends or an operator that sends a function that on the vertices to a function on the vertices. The incidence matrices, on the other hand, they send code chains from one part of the space to another part. So B12, for instance, sends a code chain that's supported on the faces to a code chain that's supported on the edges. Okay, so you can think. So if you have a combinatorial complex or any complex whatsoever that has multiple dimensions, now you can think about those incidence matrices and adjacency matrices, the Laplacian, as being the means to shuffle the data around or to send messages, the data around among all those parts of space, basically. Okay, so you can see here how the graph world is constrained. Basically, you have X naught in the graph, and maybe you have X1, and you can only send the messages between nodes and the edges, maybe backwards, and that's the space that you have. For higher order, you have all those higher order relationships, basically, and then you have the flexibility to move your with those maps. Basically, you have the flexibility to move your signal around for your learning task. So here comes the main difference, in my opinion, between graphs and higher order networks. In graphs, this distinction, the color, if you like, between various nodes, if you think about data as being supported on various parts of your graph, shuffling the data is not as natural as shuffling the data over here, with the meaning that those higher order matrices, if you like. two main parts of that I have described so far. We have the chains, the code chains, data supported on our space, and then we have the code chain maps that pass data message between cells. Okay, so given these two elements, basically you can define our deep learning framework on combinatorial complexes. So now assume that you have data supported on maybe vertices, data supported on edges, data supported on higher order cells. You can start constructing your network. Using all those incidents and adjacency and the Laplacian matrices that we mentioned, depending on your learning task, you need to pick those matrices to pick your message passing basically, and based on that you're going to define your network. So here I'm distinguishing in this figure here. I'm still distinguishing between two types of operations basically. I'm calling the way we're calling sending signals between cells of the same dimension. We're calling them message passing. This just to be similar to the message passing on graphs. We're calling sending signals from lower dimension to higher dimension. We're calling that pooling. We're going to see that for a little bit of intuition, why we're calling that sending signals from here, let's say dimension 2 to dimension 3, pooling. And we're calling sending messages from lower dimension, from dimension 2 to dimension 1. So the lower dimension basically unpooling. We're calling the general operation, we're not calling it anymore message passing, we're calling it push forward. Also, we have a reason for this. I'm going to explain it in a little bit. So they just explain the general framework for higher order message passing. What do we mean by it in just picture? So this just to give you a summary of what we have done so far. So we have a set of vertices. You defined some higher order relationships on them. So this could be your combinatorial complex, your cell complex, your simplicial complex, any complex you care about. And then depending on your learning task, you pick your neighborhoods. So this is really arbitrary. It's up to your learning task. Then you pass all these to your neural network, and you may want to infer some signal on this node over here. Okay. The way to build those networks, we find the message passing paradigm to be a little bit cumbersome, because the networks that we built became so quickly very difficult to have intuition for. So we wanted to make things a little bit more abstract and look at things a little bit from far away. And that turns out to be very useful in summarizing what's going on in those higher order networks. So we mentioned that we may have signal on multiple parts of your space. So you might have signal on nodes and edges or faces. So we're gonna just collapse everything for nodes over here, and everything for edges over here. For this, we're going to call it this C superscript 0, and here we're going to call it C superscript 1, and for faces we're going to call it C superscript 2, and we're just gonna basically draw the network like this. So instead of having it with this picture, we're just gonna put it denote what's going on as far as message passing like that, and maybe we label that also by the map that we use for the message passing. We call such a diagram a tensor diagram, and we essentially showed in a different work with Dina and Mathilda and Sophia that all current higher order networks can be described via a tensor diagram. So the tensor diagram basically form a language, if you like, to describe networks for higher order, to describe the flow of signal for higher order networks. So message passing, the higher order message passing is a special case of those tensor diagrams, if you like. So you can think about it here, for instance, as one node that that represents the vertices, and you have the flow coming from all those adjacent cells. So you have one from the faces, one from the nodes as well, and one from edges, and one from the nodes as well over here. Okay, so higher order message passing can be described by 4 equations. This is very similar to if you are familiar with the setting for just the abstract setting for graph-based message passing. So what you do first, you have if you define the message between x and y to be a function of the neighborhood nk between the signals x, h of x and h of y, and then you then you take the summation for all those messages basically, and that's going to give you m of x. Then what's special about the higher order message passing is that right now you have multiple k's basically, so you need eventually to connect those together. So we call this operation here another tensor basically. The main differences between the summation and the tensor, here we must have permutation invariance, just like in the graph case. You don't have a so you don't need to have this condition on the tensor over here. So that's one main difference between higher order message passing and a graph message passing. I mentioned that pooling corresponds to sending messages to higher order cells basically. And I think that makes sense because that's what you do in the graph case and in the image case. So in the graph case, whenever you do pooling, you actually coarsen your graph first somehow, and then you send that, and then you found a way to summarize the signals and send them to your supercells. So if you have a combinatorial complex or a cell complex or simplicial complex, and if you decide to send your signals from lower order cells to higher order cells, that's exactly pooling. Pooling is not different than that. So here I have a cell complex, a combinatorial complex of dimension 4. So I can think about those incidence maps that I defined earlier. If I have a signal on the vertices, if I want to send it to the edges, and then I want to send it farther to higher order cells, if I am just message passing this signal from using those maps, that's exactly what pooling is. Pooling is if you are coming from the message passing paradigm, pooling is basically becoming a special case of message passing from this perspective. But we decided to call those operations push forward. The reason for the push forward naming is that because you may not have signal on the edges over here. So push forward means sending a signal from the vertices to the edges in the absence of signal on the edges. Message passing, whenever you message pass between nodes, you're assuming that there are signals on the nodes and you're updating that signal, basically. Push forward doesn't assume where you're sending a signal from some space to another space, and this other space might not have signal in the first place. So we thought we should distinguish between these two. Pooling and unpooling basically a special case. So you just assume that J is larger than I, and J is smaller than J is smaller than I. So again, all this one of the things that the abstraction, what it reveals, that really message passing and pooling are really one unified operations, and that's very clear with this combinatorial complex setting. Finally, again, as I mentioned earlier, what I think is the most important part of this work is that we made an effort towards making this accessible and easy. So we built 3 packages, basically. The first one is TopoNetX. So TopoNetX clearly inspired by Network X, which is a very popular graph library. So we wanted the user to be able to create simplicial complex, combinatorial complex, cell complex very easily. So you just instantiate that, and if you want to add the cells, you just have combinatorial complex and add cell, and maybe specify the rank. That's it. And you can compute, and the user can compute the incidence matrices, the adjacency matrices, the Hodge Laplacian quickly and easily. So Network X doesn't do any deep learning computations. It's just NumPy, SciPy in the background. That's it. Topo Model X, on the other hand, supports deep learning computations on higher order networks. So if you want to do deep learning on cell complexes, simplicial complexes, combinatorial complexes, Topo Model X, we built our networks that I'm about to show you in a little bit on the top of them. And we also, we had a challenge recently, and the people who have contributed to topological deep learning in the past 2 years have contributed. They put their repositories in Topo Model X. So it's becoming quite comprehensive library for doing deep learning on topological spaces. The last one is doing representation learning on topological domains. I would say this one here is still an area that needs a lot of work. So there are, I think almost like six algorithms implemented so far, like cell to vec, simplex to vec, and so on and so forth. So if you part of doing deep learning computations on topological spaces, you must do also representation learning. So these three libraries, if you want to start in this area, give you a very good start. We have tutorials. We added data sets as well that are easy to, so you can immediately start training the networks basically. So for the results that we did in our paper, mostly the tasks that we did are geometric tasks. So we have segmentation, we have classifications. So these two networks over here, I'm just drawing the tensor diagrams. These two networks over here are segmentation networks. So you can see here the flow, the input is vertices, edges, and faces, and I'm taking the flow towards the edges. The reason for this, because I have a label on the edge for this data set, the segmentation data set there, where the label is supported on the edge. And this is very similar, except that the signal that the label is supported on the faces. So that's the only difference between these two. So these are two segmentation networks, and the classification one is also very similar. So I have the input to be vertex and edge and face signal, and I just take this tensor diagram in order to do the final classification. So here you can think about the rank 5 cells basically as being a cell that takes the sum of everything. So again here, this is again why pooling here naturally forms a generalization. Naturally falls within this area, within this area of higher order message passing. We did also some graph classification, and that's our tensor diagram over here. We did also some work with mapper on graph. I did not have time to put all the details for mapper on graph on those slides, but the basic idea is that you create for every mesh you compute the mapper graph, and then you use the cover you obtain from mapper graph to obtain higher order cells, and you pull the signal towards those these supercells in the mapper graph. So that gave us a quite simple network, I would say. And this simple network, we use those simple network to do mesh and point cloud classification. these are the data sets that we conducted our work on. So this is for the segmentation, and this is again for segmentation. And these are the results. So we compare our results to state-of-the-art mesh classification. One thing was worth mentioning here, we did not do any extensive hyperparameter. Like we just really literally tried the first network that came to our mind, and then ran the experiment on, and we reported the results. So there is no extensive training that we did over here. So we compare all those networks, by the way. It's just, again, worth mentioning that we compared against. They are very specialized towards this task. I mean, you can use, in our case, you can use it on graphs, you can use it on meshes, you can use it on other kind of things. But we just chose to compare it against those specialized networks. So this is for the classification results. Again, obtain something comparable to the state of the art. And this is the data set that we obtained, that we used for the graph classification. So we had two graph classification, one of them called easy, one of them called hard. That's the way that those data sets were called in the original paper. And again, we obtained something very, very similar to the state of the art. One thing we mentioned in some detail in the paper, there is a lot of similarity between the tensor diagrams and topological quantum field theory. And those, if you are coming from a classical topological background, those tensor diagrams, they are very, very familiar in that world, especially my background is topology myself, and those tensor diagrams are pretty much inspired by notions from low dimensional topology, where you might want to move, where you have small elements and you want to combine them together to obtain a global picture, basically. So this can be used basically towards architecture search in higher order networks. So one of the things that we find like for the networks, for instance, that the way we build them, again, we thought intuitively what might be the easiest tensor diagram, and for the learning task, and then we build it accordingly. But this might not be an ideal architecture. So you basically give this topological setting, this topological quantum field theory setting, we give an algorithm basically towards a architecture search for those higher order networks.
Okay, thank you. And also especially thank you for making this so accessible. And yeah, we can go ahead and use our own graphs and turn them into combinatorial complexes. Okay, but then do we have any more questions from the audience? I mean, we had a few pointers in the chat, but yeah, I guess one question just came up. Tensor diagrams seem to help with the same problem as integral transform from category theory applied to message passing neural networks. Okay.
I'm not sure what you mean by integral transform, but definitely I mean, you have, so I mean, you can think about, I mean, topological quantum field theory is basically a functor from one space to another space. So you can, I mean, you can think about the graph itself and the nodes as being your one category. And then what it means on the other hand, in our case here, you have a cochain and cochain maps, or that's the other space basically. So you have just the label nodes and the edges to be, that's your category here. And then you have a functor that maps that category to the other category of chains and cochain maps basically. So I mean, there is definitely categorical theory inspiration over there. And it is actually a functor. The tensor diagram that we built are actually a functor. I'm just now using this language over here.
Okay, yeah, that's the next one has me curious as well. Given a point cloud, is there a good standard way to assign a combinatorial complex to that point cloud, including meaningful higher order cells?
Yes, very good question. We skipped that. So the way we did it, we did that in the paper. The way we did in the paper, using actually a mapper graph. So you can think, take your point cloud, build a graph maybe, and then take your supercells for your point clouds for your mapper graph. So a mapper going to give you basically a covering for your point cloud. So you can think about those cells as being a higher order cells in a combinatorial complex. And you can, so let me go back to this picture I showed you earlier. So, I mean, here it's a graph. It's the same idea. It's either a graph or a point cloud. So a mapper basically gives you a way to assign supercells to your point cloud. So you can have multiple resolution for mapper basically, and you can declare those to be your higher order cells in the combinatorial complex. That's what we did in our setting. So we took the point cloud, then we took two concentric covers basically for our point cloud, and declare those to be our higher order relationships. And you can use the incidence matrices that I showed you about to define message passing. And this is the network that we built. That's the tensor diagram that we built for using mapper. So here we have our mapper. I think it has edges, if I recall correctly. So we built the graph, and then on the top of the graph, we built those higher order relationships using some scalar function defined on the graph. And then we used the incidence matrices to push forward the signal from the rank 2 cells to rank 4 and rank 5, which are those supercells basically. So this is your answer is mapper can give you way to define the combinatorial complex very naturally.
Okay, then how expensive is it to compute combinatorial complexes to compare, say, an alpha complex?
Very good question. The most expensive the condition is X is contained in Y, then rank of X is contained in rank of Y. So the easiest way to think about this, think about the Hajij graph that corresponds to the combinatorial complex. So basically you want to insert a cell in this Hajij graph such that the cells that are on the top of they're connected on the top of it, and the cells that are connected on the bottom of it satisfy this condition. So all you need to do is to keep track of each node is where it belongs, basically. So we have a dictionary that tracks where each node where it belongs, and each cells what cells it belongs to. So for our current implementation, it is a little bit slow, it's quadratic, but we think we can make it faster. And we are building something a little bit more general that's going to make it constant time insertion based. But the current implementation for combinatorial complex insertion SL is quadratic with respect to the number of nodes.
All right.
Yes, can I ask a question? So if I understand correctly, right now, this implementation is based on something like Hajij Laplacian. So it is matrix based, and thus it is dense. And because of that, if we basically need this higher order faces or something else, we kind of need to apply them everywhere in our domain. But is it possible to do this locally? So basically, for example, in something like knowledge graphs, you would have some hierarchical relations that can naturally be described with probably something like maybe even simplicial complexes, or just some set-to-set relations, which can be described as hypergraph. But those information is sparse. It can be present in part of the knowledge graph, but not everywhere.
Yeah. I mean, by no means what we described with those matrices are the only matrices that you can use whenever you want to define message passing. These are only examples. This is why we said this is really up to your learning task. We picked the most generic ones because that's the ones that people are familiar with. The incidence matrix, I mean, what comes to your mind whenever you want to do message passing? The adjacency matrix on graph. That's the most natural one. But there are gazillion variation of these in the graph neural network. Like it can, there's so many ways that you can basically generalize this. But yeah, I mean, what you mentioned is completely justified. You don't have to use any of these. You can use your own for your own specific application. But these are the ones that came to be, that we thought are to be the most people might be familiar with, basically.
Yeah, my question was, I think my question was a little bit about a different thing. It was more about applying this push forward iteration that sort of lifts us, broadcasts our data to higher dimensionality. So for example, from nodes to edges, or from edges to faces, but do it not everywhere on the graph, not on every target node, but on only partial set of nodes that are the most complex ones, sort of.
I see. Oh, I see what you're saying. But wouldn't that be the same as defining other types of relationships in the way that you describe them, and then you define the adjacency between those the nodes, and you're saying don't define. I see what you're saying. Don't define the adjacency between all nodes and all higher order relationships. Define the adjacency between partial set of the nodes to partial set of the higher order relationships. Is that that a question?
Yes. So I kind of understand how it can be done before computation starts, like in terms of graph topology. But I think it's a very difficult task to do it like continuously, so that backpropagation would work. But it's interesting.
I think the answer might be basically first to constrain your domain to a subspace of your space. Then you compute the instance matrix on that subspace, basically, and then you do message passing. I think that would be equivalent, basically, to just constraining, then do the classical setting that we did over here. If I understand.
I think probably that's the best option. Thank you.
Okay, very nice. So I did not only learn about this paper, but a lot about topology and topological deep learning in general. And if you want to keep learning like that yourselves, then join us in future reading group sessions. And maybe see you next week. I'm looking forward to it. See you.